So how's everyone doing? We're post-lunch coma, right? So hopefully this one will be pretty interesting, maybe entertaining. So we're going to talk about acoustic side channel attacks. So yeah, this will be pretty cool. So my name is David. If you were here yesterday in the other hall, yeah, I'm kind of doing AI. I've been doing it for a while. It's very fascinating. I love doing it. I think there's so many cool and interesting things that you can do with it. And yeah, I kind of have a weird background, kind of all over the place, storage, working on virtualization, did a lot of open source Kubernetes, and then like 5 years ago, got into the AI and ML thing. But yeah, that's kind of a little bit about me. So we're going to talk about acoustic side channel attacks, and the agenda, we're going to kind of cover this weird moral duality with AI and ML. And I kind of want to just start with that because it's kind of important, especially in this day and age, especially after the keynote, which was amazing. And then we'll talk about, literally, how to build an acoustic keystroke logger. And the slides, and scary enough, the code to do this will be in my GitHub repo. So, and if you don't want to go through the training to train the model, the already trained model will be made available for you. And so we're going to talk about the 3 very technical slides of like how to build this thing, what the architecture looks like. And then we'll do a lot of demos. I think there's 5 of them. And then we're going to talk about real world attack vectors, what you could use this thing for. And then we're going to talk about what to do about it, like how to protect yourself and your privacy, and possibly even how to disrupt this kind of stuff. And then we'll have some Q&A at the end. So let's start off with the moral duality of AI and ML. So here's a tweet from Elon Musk. You know, he's got this super extreme positive outlook. You know, a lot of people, especially in the news, you see everyone's kind of very fearful of AI and machine learning. And you know, you have Elon Musk here who says, oh, don't worry. Like, it won't be basic income. He says, things will get so cheap with AI that everyone will have universal high income. And I would love to believe that. That would be awesome. But kind of just looking at history, that's probably not going to be like that, right? Otherwise, we'd all be sharing and everything would be all great. And if you look at the flip side of it, you see like this MIT study that says AI can already do 11.7% of the jobs that are out there. And another scary statistic is that you have the number of programmers have hit the same level as back in the 1980s, which is scary. And there's this extremely hopeful outlook on AI, and then there's this extremely negative. I think it's going to end up somewhere in between, but kind of my advice or my suggestion for everyone is like, it's here, it's not going to go away. I would encourage you to take a look at it. Use like ChatGPT or Claude, whatever it is, whatever AI or ML system, just kind of learn how it can help you out and help you make your life easier, because unfortunately, it's probably not going to go away. Now, some of the very interesting and very cool things that AI can do. Here is it's an NIH article where AI is literally coming up with new ways to cure disease. And so here's like an article about an NIH article saying, hey, AI is pretty cool. I mean, if you kind of take this to the end, it's going to, who knows, we might be able to cure cancer and maybe there won't be any more disease, right? So it has extremely good applications. And it also has very extreme negative consequences. So a lot of people don't know this, and everyone's talking about inflation and like what's happening, like why is everything's cost so much? there's literally companies out there that are trying to figure out how to maximally extract how much you're willing to pay for things. And I would definitely click this link down here, this video, and just take a look, just open your eyes up that some of the inflation stuff is greed for sure. Like probably a lot of it, most of it if I had to guess. So this is like the extreme negative of machine learning. And I kind of want to bring the light because we're going to get into a weird topic where I'm going to literally tell you how to build a keystroke logger from Acoustics.
That's happening in grocery stores.
Oh yeah, that's what those digital tags are for. Thank you for saying that. Yeah, those digital tags, so based on the time of day, they will update the price because that's when most people hit the grocery stores. And when certain times when it's like lower or whatever their algorithm says, they'll drop the price so that the price is cheaper. And if you use apps, like you're gonna get a different price than what's in the store too. So just be aware of all this stuff that's happening, right? So this session is literally based on this archive research paper. It's a practical deep learning based on acoustic side channel attacks on keyboards. And they basically created a machine learning model to, when you push a button on the keyboard, just on the acoustic signature alone to determine and figure out what key you're pressing on the keyboard. And this is where we're going to start kind of this discussion in this session. And I don't know if it's good or bad. I improved on it a little bit. So yeah, I'm gonna describe it. I'm gonna tell you exactly how, and also hopefully how to like defend against it. And one reason I'll kind of get toward the end, like why I'm giving you the code to do this. In order to disrupt, you need to learn. And so that's one reason. So let's go ahead and start. So building an acoustical keystroke logger. So it sounds wild and it sounds crazy, right? That you can literally build sound classifiers to classify sound, like different types of sounds. But in reality, this has been happening for years, and many people are doing it. And so kind of like the process is you have sound and you need to record it. And you need to have a lot of recordings, and a lot of people, you record it. Most of the time it's a WAV file, could be MP3, but typically people use linear 16 wave, and you convert that WAV file into images. And so in the upper right-hand corner is what a WAV file looks like in pictorial form. You can see the frequency and intensity, which is the frequencies on the y-axis, and then over time is the x-axis. And so this is what a pictorial representation of a sound is. And if you look at the picture just below that, there are many different types of sounds in each one of these squares. But what you can immediately see just looking at it, that there are certain patterns that are there, right? And so those certain patterns you're seeing, like the one right here and the one next to it, you can probably just looking at it say, hey, these two sounds might be very similar. They might be the same thing. Whereas the one next to it, it's obviously very different. So it might be a different sound. So people have been actually doing this for quite some time. Starting simple, dog barking, cat meowing, you can be able to tell the difference between the two. Even environmental sounds, I know that the last one is there's actually an application of this for recognizing gunshots in urban settings and being able to distinguish the difference between a gunshot versus a car backfiring versus a firecracker. I live in Long Beach. Every day there's a firecracker. It's ridiculous. But being able to make the distinction between those, so maybe you can signal to the police saying, hey, this is actually a gunshot and we need to send someone in this area quickly, right? So this has been happening for quite some time now. And just to give you other applications, so last year I gave a session at AI Dev in Amsterdam, and this was actually recorded. The GitHub repo is still there, but I actually created a multimodal model to do sarcasm detection. So you can actually find out whether someone, it's not 100% perfect, it was actually the confidence level was approaching 80%. Well, using, well, so using the data sets that were there, which we basically used, I used an existing data set that was for like Big Bang Theory, Friends, and stuff. But you can, just like you're saying, there are definitely, it's not ever, nothing's ever 100% perfect. And actually, I ended the session saying like, if I took something that Aubrey Plaza, who's very deadpan, and ran it through, it would come back, she was serious every single time. And so, you know, there's a lot of flavor and uniqueness that we as individuals all bring. And so, sometimes it will work and sometimes it won't, but it's still a very interesting application of using acoustics and also facial, like seeing eyebrows, you know, when you make gestures, and as actually using machine learning to do the voice and also the facial affect changes, like your eyebrows raising and all that stuff. But it was recorded. I would go ahead and take a look at that. It's pretty cool. We're not going to watch that though today. So if you saw my session yesterday, it always starts with the data set. And we're going to use two data sets, in fact, actually, because we're going to solve two different problems. So the first problem is, it's a data set keystroke noiseless final. Apparently it was used in some academic, potentially like contest where they were trying to do this exact same thing. And it was using a single keyboard, so we didn't vary the keyboards. There's actually one keyboard that was fixed, stationary, used for the training data, the validation data, and the test data. You don't need to worry about it. It was just a single keyboard that we used. We're trying to detect sounds based on a single keyboard. Then the second data set, which is the one right below it, and these links work so you can actually go download the data sets yourself if you want. I also provided links in my GitHub. But the second one is multi-keyboards. So it was like 5 or 6 keyboards, 6 keyboards of all various different types of manufacturers, like I think Lenovo, MacBook, some other ones. This might sound frightening. Lenovo over Zoom, Lenovo over Messenger, I think was the other one. So different keyboard sounds, whether you are physically there or on the other side of a different laptop. And I pointed to both of these research papers so you can kind of like look at yourself to see like kind of like what their kind of conclusions were. Obviously, the multi-keyboard problem is far more difficult to crack, right? Because different sounds for different keyboards. And so now therein lies the problem for that one. But two different problems, single keyboard, multi-keyboard. So we kind of already talked about a little bit actually about the data processing pipeline, how we start. So we need a lot of recordings, and those links provide WAV files for, the first one was, I can't remember what keyboard it was, but it was multiple clicks of every key. I think it was like 6 or 7 times for every key on the keyboard. And then the multi-keyboard data set was multiple keyboards, multi-clicks for every key on every keyboard, right? And we need to take those WAV files, turn them into that pictorial spectrographic image, frequency over time, with intensity, and the colors all matter. And we need to create classifiers so that when you hit a button, we classify what letter is being pushed when you hear the sound. Yes? We'll get into that. You're jumping way ahead. No worries, for sure. So if we're trying to classify all these sounds, we need labels for them. So, right, A through Z, 0 through 9, space, enter, and we're only going to look at 38, and it was just for training for the training time for all this stuff. But we're going to do frequency over time. We have 3 different channels because it's a color picture, RGB. And we're going to fix the size of the picture so that every picture is the same. We're going to normalize some stuff because maybe the key press isn't exactly at the start of the WAV file, so we're going to like shift things over and do all sorts of fun stuff. Basically, we're going to try to make it so that it we can train with adding variability so that we can hopefully classify these different keystrokes. So here's actually these are the 3 slides that are most nerdy and very technical, and then we'll move away from it. So the model training. So we used a CoatesNet style architecture. It's just a neural network that does depth-wise convolution and self-attention. Remember the word attention from yesterday? So we can go back over what was previously important to like what is relevant as we're processing the sound. But ultimately, we're kind of like using local patterns and global context. So local as the frequency starts to change as we progress through time, and then take in the final picture for the entire image as a whole and try to find the patterns both in time and as a whole. And when we're training this, we're going to do something super, and I didn't invent this, by the way. I'm using literally the stuff that was used in that research paper in the beginning. So I didn't like do any crazy hand-wavy stuff. So what they did was they trained it for an very unusually high amount of epochs. And an epoch means you have all of your data, and you're going to do one epoch is one pass of the data. And we're gonna do 1,200 passes of the data at a very small learning rate to find out what little things make this thing very, very special to make this like the sound for the letter A. And so that's kind of like the very high level version of like what we're doing here. There's this other fun stuff, optimizers and whatever, which we'll just skip over. So the first problem, acoustic key detection, single keyboard. So we have training data, which is we need to learn like what the sounds sound like for every letter on this one keyboard. And then we have validation data, which basically says for this letter A, we have validation data, so another sound for a different instance of a key press, and we're comparing the two, and we're basically trying to get these two to converge. And then we have test data that says we can test it to see how close are we to getting these two things to converge to 100%. So the goal is, you hit a button, you want it to be 100% certain that that button press is the letter A. But we're only using a single keyboard, which drastically reduces the scope of the problem. So very fancy words, single keyboard. We just want to make sure we hit many keys on a keyboard, and we want to make sure that we get the right acoustic signature and the right classification for A through Z, 0 through 9, space or enter. So instead of just talking about it, we're going to demo it. Because talking about it's kind of boring, right? So in my GitHub, which you'll have, and you don't need to take pictures of anything, the slides are also in that GitHub too. So you'll have the links to click and everything. So the first thing we need to do is we have a bunch of WAV files. We should go data. We'll just look at the training data for one. And I've obviously reduced it. We're only going to look at the letter A, because otherwise this would take forever to do. And so if we do an LS of training data, the training data and the letter A, you can see that we have roughly 8 sounds, or 8 different WAV files for different instances for the letter A. You're pressing the letter A, record it. Press the letter A, record it, over and over again. So we need to convert these WAV files to spectrographic images, right? Those pictures. So let's go ahead and do that. And because I can never remember these commands, I have this cool little thing that will just copy and paste. Oops. Is it just a lot? I have too many. Oop. So pretty quick. And if you see, it's in the images folder, right? So we converted those WAV files to images, and if we do an LS, there's now an image directory. Actually, let's just go ahead and look at one of them to prove that I'm in right. We did training, the letter A. We do an LS. We have PNG files. If we open one of them, super small. This is the letter A. And that's just one instance, right? This is the letter A. Different, but different instance of it, yeah.
What's the resolution of the wave versus the PNG pixel count and stuff? Because the image was.
Yeah, and it's intentionally like that. So it's chopped off so that every wave file is exactly the same length. In machine learning, when you need to compare things, they all need to be of the same length, same dimensions, same, like whatever it is, like whether they're pictures or if you're chunking text, like 2K or 512K, right? I can't remember off the top of my head. You have access to the code. Definitely, you can take a look at it later. I just don't remember off the top of my head, sorry. So we have WAV files to PNG files. So let's. No, fixed. Yep. Yep. So now we've converted, well, we've done the sample set, but we've converted all of them to PNG files. So if we actually look at our data and go, okay, yeah, sorry, I've already divided it out. So if we, not org. So train test, I'm just gonna look at training data. All of the different keys, I'm just gonna pick a random letter, letter N, PNG files, right? So every letter, we have multiple PNG files for every letter so that we can train our machine learning model. This would obviously take far too much time, but to train this model, Python 1_train, and it will build it. I would advise you using an H200. It will take roughly about 14 hours. But it is there. So you can train this and build it. And if you don't want to do that and burn your own money, you can download the models. I've provided the link that's already built. So you can do this on your laptop at home. And we have one WAV file here, s-09.png, which represents the key press S. And we're going to now take our model, we're going to take our image, run inference on it, and see what happens. And again, this is a single keyboard. We'll get into it. Yeah. It's just like, you're jumping ahead. You guys are smart. So take the keyboard, run it, or take the picture, run it through. 100% certainty, I know this is the letter S. Single keyboard. So if you're using a single keyboard, we can actually pass it through this machine learning model. It will guess 100% certainty. Cool. Or I guess not cool, depending on your take of this. So, single keyboard, we can actually, believe it or not, with 100% certainty, be able to classify what keys you're pressing. Now let's look at, can we save the questions to the end, because I'm gonna run out of time for sure. Multi-keyboard, so we have multiple keyboards. Lenovo, Apple, HP, MSI, over Zoom, I can't remember which one it was, and then over Messenger, I can't remember which one it was. Just goes to show you as you're typing, don't have your microphone unmuted. So now we need to do the same thing. The previous one was a single keyboard, now we have multiple keyboards, so the problem's far more difficult. So we're going to divide all of the sounds for all of the keyboards, training, validation, test, right? And we're gonna train our machine learning model to hopefully guess multiple keyboards. So let's go ahead and give that a try and see what that looks like. Just like before, Python 1_train. This will build the machine learning model from scratch. And I will provide the download for the completed one so you can just run inference at home. And before everyone gets freaked out, keep in mind that these keyboard sounds, right? Not like just generically anyone's keyboard. Okay. So we're going to run inference on it, and for this one, oops, we're going to use the Lenovo 5 PNG H, so the letter H. And we're going to take that image file and just pick one randomly, and keep in mind that this machine learning model has been trained to detect 6 different keyboard sounds, 2 of which are over a remote meeting session like Zoom or something like that. And we're going to pass that keyboard in, or that sound for the letter H for Lenovo, and see what we get. Now, notice that it's vastly different, right? The other one was 100% certainty every single time I can figure out that this key button is that one. Now, what's very interesting is if you look for that image, still the #1 slot is the letter H with 48% confidence. And I set the top K equals to 5, so we can see what the top 5 guesses for our machine learning model are. The next one's G at 24% confidence. The next one's J at 16% confidence. The next one's K, so on and so forth. So keep this in mind because it will be important a little bit in a second here. So we can see that the confidence score drops dramatically once we start to introduce multiple keyboards. And although this one happened to guess it exactly right, not exactly right, but I mean, with the 40% confidence, 48.6% confidence, it can guess the letter H. So, but we have these little nuances because now we've introduced multiple keyboards. So, let's see. What did I do? Hang on, sorry. Yeah, I always forget which one. Okay. Yeah, it is this one. So, now if we wanted to simulate what typing is, right? You know, typing multiple letters with the multiple keyboards data set, we're going to spell out a little message, and we're going to enlist the help of these sounds to simulate me typing something on a keyboard. I just picked one, the Lenovo keyboard. And you can see the different images that we're going to use and pass through our model. The letter A, C, D, E, H, and so on. And we're going to spell out a message using these images, which would correspond to sound. So it'd be effectively, if I were typing on a keyboard, I'm hitting a button, the sound can be picked up, we'll pass it through the machine learning model, it'll tell us what letter it thinks it is with the confidence score, hit the next one, so on and so forth. And we're going to try to spell out a message and see what we can do with this. So, you can probably figure out what I'm trying to say right here on this side right here. So, hello SCaLE. So, we can see that the first letter is H, 48% confidence. E, 69% confidence, LLO, space, DBSLE. So it wasn't able to get all of it right. But there was a reason why, and this is actually where the paper, not failed, but maybe lack of imagination or whatever, they were trying to get the thing to give you the letter as this is the most confident letter to be selected, and there was a reason why I picked a top K of 2, because you can actually get SCALE, right? So I increased the top K to 2, basically saying, okay, D is not correct, but S is. So how can I use this to my advantage to figure out what someone is saying? And so I'm going to do a live demo. It's going to hit the internet. So there's something very interesting here. Like, most of the keys on your keyboard are all kind of the same, right? Like, they're, the same shape, right? What is one key that is very different from all of the others? Got it. So I don't need to test every permutation to figure out what this message is spelling out, I can delimit it by space, chunk the word so that the word is here, space is a hard delimiter, look at the next word, and now run just the permutations on just 5 letters versus the entire string. And so that's what we're actually going to do. And we're going to do this, I'm going to hit the internet, I'm going to take every combination for the first 5 letters, we have a space delimiter, then do every combination for the next 5 letters, and I'm going to run it through a spell check to give me actual words, right? And what we're going to do is we're going to do spell check. And hopefully the internet will work. I'm hardwired this year, so hopefully it will. But we're going to run through every permutation to give us my firewall. And every complete word, we're going to output it to the screen and also save it to the file. Hello. Well, we already knew that, right? If we look up, we can see that the first letter is H-E-L-L-O, right? Top confidence score, right? And so it's now going through 32 different combinations, 5 letters, right? 2 to the power of 5 is 32, right? 32 different combinations. It's going to run through, find every potential combination, hit the space bar. Now we're going to take the next 5 letters, SCaLE, what's supposed to be SCaLE, and we're going to run those 32 combinations, same number of letters, 5, and we're going to run that through a spell checker too. This is going to take a little time. I know this is probably anticlimactic here. Keep going. Okay, cool. And I'm actually going to output like some of the potential words, but we already know that hello is one of them, right? Because we can see complete hello. We know that's a word, we just threw it out there. Plus, it's also the top most word that's the confidence score on. That's from the spell checking API. I forgot which service I used, but it was free, so I just ran it through. Now we're looking at the second word. We're using the space as the delimiter because it has a very unique sound, because it's the key is very different, and then we have SCaLE, right? Complete word, and and it's going to go ahead and it's going to chug through every other key to try to figure out what other words there are. And I could have made this a lot more intelligent, like obviously able is a word, but it's only a 4-letter word, so I could just junk that, right? Because we know that there are 5 keys, and we got a 4-letter word, that's obviously not it, throw it away. And then if we do a cat on our, which we already know, completed words.text, which is dynamically throwing it in there, hello SCaLE. It doesn't need to be perfect. It needs just to be close enough to get to where you need to go. And then implore little things to say, hey, think outside of the box. How can I get that to get closer and closer and closer? And so that's, whether it's good or bad, that's the improvement that I kind of realized and made is don't just look at top k equals 1, maybe top k equals 2 or 3, and then try that in different ways, right? So, then it occurred to me, if you're typing away and you're listening to all the sounds and you're trying to use brute force to figure out what these words are that might not be 100% perfect, like, it's going to probably screw up every once in a while, right? And it's going to be like, give you a garbage word or a word that's not a word, or maybe it doesn't even make sense. So if you saw my session yesterday, I created a masked language model, which basically says, hey, I think this word is garbage. I'm going to omit the word in the middle of this sentence, and I'm going to use AI to help me figure out what that word, the most probable word to fit in that location is. So basically the idea is I want to be able to figure out what this person is typing without actually intervening at all and have AI do all of it. And so the purpose of a masked language model is, if you've done Mad Libs before, you have a sentence, you have a space, and then you kind of want to be able, the point of Mad Libs is you put in a funny word and you're all supposed to have a laugh. But we're going to, instead of making a funny word, we're going to find the most probable word to fit in that location. And so This is also in GitHub too, to train this model and build this model from scratch. It was in my session yesterday. We're just gonna run inference on it. And we're gonna pass in 2 sentences. So they're just example sentences, right? That says, the capital of France is blank. This is the same demo I did yesterday. And the blank, the most probable word is Paris, right? The capital of Paris, or capital of France is Paris. Distilled models are the blank of large language models. They are the smallest of large language models. So if you came across a word that might seem like garbage or not correct, you could put in a blank or a mask for like what that word is, and then try to have AI fill in the blank for like what maybe the most probable word is, so that you don't have to intervene into trying to figure out what someone is typing on their keyboard. So let's summarize all this. On a single keyboard with 100% accuracy, like you can figure it out, right? So if I collected the sounds on my MacBook here and only had the MacBook and trained a machine learning model 100% of the time. Multiple keyboards, I ran it through, I used all the test data, ran it through, and it was only 46% accurate. 46% is actually, if you think about it, it sounds low, but it's actually pretty dang high. Because if you did a normal distribution, if you guessed randomly what the key press is, it would be 1 out of 38, which is 3%. So almost half of the time, the most probable answer would be the right key. And maybe the second one, maybe it's not the first one, maybe it's the second one, or in the worst case, maybe it's the third one. But that's still pretty crazy. So what we did was we basically said, hey, let's consider the second most probable or the third most probable and try to like work backwards from there. And then use AI in that last demo to fill in the blank for words that we know were garbage. Now what we did not test, and this is where you can sleep better at night. So we did not train a machine learning model, and we did not introduce a new keyboard. And I don't need to do that test because I know that would fall apart very, very quickly. And the results will drop dramatically, like very, very dramatically. And if you want to look in more detail about that, the sarcasm video that's recorded, I actually did this independent dataset test, which is I introduced a whole new comedy TV show to detect whether it's sarcasm or not. It was actually still good, but it starts to drop off dramatically, and I didn't need to do it here because I know it would be way more drop off than before. So I didn't do this one. I didn't do the next one either, but I think this would be very interesting. What if I took a MacBook or a keyboard manufactured in the same lot, and I'm basically banking on the fact that the manufacturing process to build these keyboards are so identical that I might be able to use maybe this keyboard to capture the sounds, but in the same lot number be able to see if I can guess what number the key press is on that. And to your question, I actually have this picture right here on the right-hand side. This is the frequency in which you would normally press keys just from normal typing. And it's actually a well-known thing that you hit certain keys more than other ones. And so what I'm saying here is, like the letter E is the most important, like most pressed key. So what I'm actually saying here is, because we know the frequency of how often we hit keys, maybe the wear and tear on everyone's keyboard is all the same. I didn't do this, but it's a very interesting thought experiment, right? So some of the improvements that we could do, which is getting to, I forgot which is your question, the things that we could do to potentially maybe even improve this even more, not that I'm going to get in trouble by the NSA or something already. When you type naturally, you flow from one letter to the next letter, and by changing the variability of your hands, maybe that has some sort of change in the way you might hit the next key. So what you might actually need to do is you have an understanding of what you hit before to better predict what you might hit next. And I think so. The other thing was, maybe the person could change based on, like, I think it was like man versus woman, or different people hit keys at different strengths or whatever, and maybe that has something to do with it. But you're still hitting the same key, so maybe you just need to do even more training with a larger sample set to try to even figure that out. And then you have the idea of like multiple users. I know most of us was taught like to type on home row. I don't do that. I weirdly memorized the pattern of what the keys are on the keyboard, and I like peck at it like really fast, but I don't have home row. So I'm sure that would affect it too. But kind of the point is you need to record all of that stuff to try to teach the model to recognize all that stuff, right? And to filter out the stuff that is not important, like that variability, to find and hone in on the unique thing about that key to make that key press recognizable or classifiable. And then there's also noise, right? Background noise that could add into it. So real-world attack vectors really quickly. So this isn't a new thing. This is actually really weird and fascinating. So there was a toy that appeared in Captain Crunch. It was a whistle. And this whistle, when you blew into it next to a payphone, it would actually give you free calls. This is a side channel acoustic attack. Back in the 80s, 70s, 80s, probably 90s still worked, I'm guessing, because they were all data-tone based. So it's not a new thing. It's just a different application of the same thing, right? So, not that I'm trying to like do bad things here, but if we were to manufacture an attack using a single keyboard. So let's just say we need to do something evil, and you need to have a single keyboard to try to make an attack on that particular keyboard. Like what kind of keyboard would you attack? This is the first thing that thought of. Everyone uses that same keyboard, and you could like walk up to the ATM every day, hit the 1 a couple times, record the sound each time. Next day, do 2, 3, 4, whatever. Again, I'm not trying to like come up with something crazy. Like the credit card readers that you put the covers to get the pin thing, so that when you slide your card in, it also reads the magnetic strip, you know, like people that are trying to steal your credit card information, put a microphone in it. Right, and record the sound. The insert of the card triggers the recording listens to the keys you're pushing, boom, you can tie the two together. Frightening. Multiple keyboards. So, like we already said, you can't introduce a new keyboard because we need to actually find out what the unique sound for that particular keyboard is. So, this one's a little more difficult, but you know, if you have your keyboards out and someone has the patience, or maybe there's that manufacturing similarity, maybe they can get all of those sounds, capture them, and then, you know, listen over Zoom or whatever the heck it is. And they can listen to what you're typing even over Zoom. And this is just kind of like a wake-up call, right? Just be very aware of like what's happening in your surroundings. I test the ATM thing every time, even before this. So just be aware, right? So now that I've frightened the crap out of everyone, protecting yourself, privacy and security, right? Like, what do you do about this? Two-factor authentication, please do it. This is the wake-up call, right? This is Yubico, YubiKey, whatever you like to use it. I would not use SMS. It's still better than nothing, but because there are ways of doing femtocells and anyhow. Use two-factor authentication, whether it's the Google Authenticator thingy, you know, the little QR code where you have to type in the number every, 30 seconds or whatever. Use something. Use passwords you don't know, right? If you don't know the password, right, there's no way anyone can socially engineer what your password could be based on your kids' birthdays or what your interests are, who your favorite football team or whatever is, right? They can't socially engineer it if you have no idea what the hell your password is, right? So use something. I would recommend using something offline because things can get hacked and things get leaked. Make sure every single password for every single service is different. Do not use like one password for all your credit card companies, because then one breach of one now cascades into all the other stuff in your, whatever you use. Change your password frequently. I know everyone hates you need to change your password every 90 days from your company, and you look at it and you're like, oh, I gotta something else. Change it frequently, right? Now this is gonna sound weird, and this is actually kind of like the point of maybe this session or whatever. I kind of like live by this motto anyways. Be intentionally difficult. Not to the point of like a harassing or whatever, but be difficult, right? I mean, there are some things that I implore, like that I do every day to, sometimes it's not even on purpose, like as I'm typing in my password, I screw up and I backspace, but even weirdly introducing errors on purpose could be enough to throw off some things, right? And so I'm just saying, be intentionally difficult. The whole point of machine learning is to figure out patterns. Be the anti-pattern, right? Yeah. So this seems cool. Apple acquires a new startup using wearables to interpret facial skin micromovements. And there's a US patent for it. And the stuff that's coming out of tech these days is crazy, especially with AI. But when I saw this, I thought exactly this. If you're talking about microfacial movements, you're literally talking about the ability to lip read, right? You don't even need audio in order to figure out what someone's saying. And especially with all these new wearables that are coming out where like the necklace thing, I'm sure OpenAI, I think they have a necklace thing. I think Apple wants to put in cameras in their earbuds now. Be aware of your surroundings and like what's happening in the world, right? So that brings us to resources. So everything, code, all of it is on my GitHub. And why I'm giving the code away. It's like I said, it's not something new. It's not something I invented, but I think it's important. I hope that maybe some of you will take the code, figure out ways to disrupt this, right? Figure out ways to like put a monkey wrench in all this nonsense and make it difficult for people to do these things. There are maybe creative ways, there are maybe technical ways. Yeah, so everything you saw to be able to do everything I did today and all the demos is right there in my GitHub, including the slides. The original research paper, the sounds, the data sets for the single keyboard, the multiple keyboard. I included the link for the sarcastically speaking, so being able to detect sarcasm. So you can click the video, watch that, it's an hour long, it's pretty cool. Also, I'm gonna throw in this one here. I did a session at We Are Developers. It was called Confuse, Obfuscate, Disrupt. It was basically being able to confuse AI enough to get it to do things that it's not supposed to do. And there are definitely ways of going about doing it. Some of them are super simple, like misspell a word intentionally so that it can't recognize that it's a certain word. You get your intention across, but it might be able to disrupt the AI to have its guardrails work correctly or whatever, right? I can tell you, I would definitely go ahead and give that a watch. Not that like trying to sell my session or anything like that, but I mean, honestly, when all these AI agents start popping up, I'm getting a discount on stuff. Right? For people that are building these AI systems and they're not kind of like building in the governance and the security, yeah, I mean, do with what you want, right? Against some of these corporations. And that's it. Thank you. That's probably going to get me in a lot of trouble, but it's all good, I guess. So question, anyone have any questions? Yep. Yeah, that's a great question. So Yes. So like what is the differentiation between like the keystrokes and like what maybe potentially between keyboards and like what can we do to potentially maybe address this or fix this type of situation? Roughly about-ish. Yeah. So oddly enough, like the MacBook keys, that was much more difficult because they tend to be quieter. So like using quiet keyboards is definitely an advantage. So the silent keyboards are great. That will definitely cut down on it. And then, yeah, it's pretty wild. Oh, the other thing I mentioned too is like, I mean, didn't mention was, as you're typing your password, cough. No, I'm serious. Like you see in the spy movies, they turn on the radio and to talk about their clandestine whatever. I mean, that's what I'm saying. Like, be intentionally difficult to like. And I know that might sound overly paranoid or whatever, but like silent keyboards, that kind of stuff. Maybe keyboards that are not used every day. I know everything gets manufactured in mass, but yeah, it's hard. No, it's not a manufacturing flaw. Like every keyboard has a particular sound, right? And if you like, kind of like that picture with all the keystrokes and how often you press every key, like the letter E is the most frequent one, you're going to add wear and tear on it, and it's still going to have a sound, but it's going to probably make that sound, I'm theorizing at this point, very close to a keyboard that's manufactured in the same lot. I'm guessing that the way we manufacture things are so close together that it will probably, if I had to guess, if I had a data set to try it, I would love to try it, but I bet you it would actually come out pretty dang close. Yep.
So there are different keyboard manufacturing styles. There's the loud click
Mm-hmm.
ones that have the replaceable keys, and then Apple's scissor keyboard mechanism and all this, and then there's also what surface you're typing on. Are you on a wooden desk or a big whatever, right? So you said everything starts with the data set. So
like,
a crowdsource controlled set of experiments to record a lot of these may provide enough information for
potentially, yeah.
It hasn't already done it.
Yeah, and like the whole point of machine learning is to recognize patterns in the data sets. And if you think about, I'm going to get a little technical here. If you think about like how the loss function works, you want to be able to get the loss function to like get your loss to be near zero, which basically says I can predict this with greater certainty. So the ML framework is designed to try to get rid of the noise and to find out the actual things and the frequencies and the pitch and all that stuff, to find out like what are the things that are common to this particular keyboard and this particular sound. So, which is scary because like that's what the framework's supposed to do, which then encourages or makes this possible, right? So even like subtle little nuances that, when you're hitting this particular sound, that AI, that, PyTorch is literally designed to figure out the little nuance that says, oh, this is the letter A, right? And it's wild to think about it, but that's what machine learning does. Find patterns in things. Yep.
So earlier, at the end, you listed like that you had 46% accuracy with multiple keyboards. Was that before or after you applied your extra techniques and like cell checking?
That was before.
That was before.
Yes.
How much were you after you added?
Yeah, so I kind of only did like a small thing, like a small set. I could probably look at it a little bit more, but I would assume that it would get much better. And weirdly enough, like the longer and more you type, like paragraphs, many sentences or paragraphs or whatever, you're definitely probably going to have gaps, which is why I use that other model to like try to fill in those gaps. Yeah, I think it would still get there using a set of known keyboards. I still think it'll get there within the top 1, 2, maybe 3. I would probably, if I were trying to build this in an automated way so they didn't have to interact with it, I would probably limit it to top k equals 2, only consider the top 2 most probable, any word that was kind of seemed like garbage, I would punch it out, make a gap, and then have it try to fill in, right? And hopefully it wasn't a word that was super important, right? And then there's something to be, you can do human in the loop, right? You can still take a look at it and say, there's this word that's roughly, or that's literally 10 characters. You know, maybe your intuition says that they were talking about this based on the overall context of the thing. So you could probably even potentially build a machine learning model to try to, based on the entire context of whatever, to try to even improve that guess, yeah. Cool, yeah. And then I'll get to you, and that might be the last one. Yeah.
Yeah, I was wondering about the images.
Mm-hmm.
You converted them to image files in the very first thing. It's interesting. Can you talk about why you did that?
Yeah. So actually, in the sarcasm thing I did last year, I actually didn't do that. I actually used, it's ended up being like 200 rows where I was using frequencies where it measured RMS, jitter, this, that, and the other, because those things are far more important when you're trying to do sarcastic things. This was a far simpler problem, an easier problem, as scary as that sounds. And the converting it to images is basically because these images are RGB, right? They're color-based. Even the change in pixelation between pixels, like the neighbors around it, and the color change can does represent intensity. And for machine learning models, it's actually much easier to train on images than it is to do text. So, and actually there's this weird cool study where people think that, or not people think, I forgot, I think it was the people who did Quen, it was either Alibaba or the other one, where they actually want to take the text, convert the text to images, and then do inference on that, and that's actually uses far less tokens. It's because images are much easier to figure out patterns for machine learning. Yeah. Oh, sorry, I forgot you.
Supposing you had an unknown keyboard, but you have recordings of a lot of keystrokes from that keyboard, is there a similar technique that would sort those into bins where you become terribly confident these are all the same key, I don't know which one, but they're the same, and I have 38 bins, and now I can apply cipher crafting software?
100%. Yep. Now you're already trying to improve the bad thing. Now you see how I got started, right? I was like, dude, how can I fix this problem? Anywho, so if there are any other questions, I think we're probably at time anyways. I'll be happy to take more outside, but yeah, I hope you enjoyed it. It's very interesting to me, and hope you learned something. I don't want to scare you, but just be aware of this stuff and hopefully defend against this stuff. Try to break this stuff is kind of the intent. So, cool. Thank you.